Nowadays, in any electrical device, we can find transistors, which can be compared to the atom of modern-day computing and open the door to the information age in 1947 by its invention. But the computers exist before transistors did. In a rudimental form, they occupied entire rooms, weighed thousands of pounds, and for all that were not more powerful as a cell phone we can fit in our pockets today. These rudimentary computers work with thermionic bulbs, also called vacuum tubes, which nowadays are more or less obsolete, but in their time they were critical to the design of many electronic systems. The principle that allows thermionic bulbs is also called thermionic emission, which is the main topic of this video. This effect was first observed in 1873. Professor Frederick was investigating effects associated with charged objects, and he discovered that a red-hot conductor would readily lose a negative charge but hold a positive one. Lately, in 1883, Thomas Edison experimented with this phenomenon during his attempt of creating the incandescent lamp. He noticed that the inside of the glass envelope became blackened. Edison built during his experiment lamp bulbs with a second element into the envelope, either a wire or a plate, and showed that when this extra metal electrode was put at a negative potential relative to the filament, there was no current between the filament and the electrode, but this was reversed to a positive potential. Then a current flowed in the circuit if the filament was sufficiently hot. And he also found that this current increased rapidly with increasing the potential. This current going just in one way was called Edison effect and was established in a patent application for the first voltage regulating advice.
Metals are a group of materials that show special behaviors in their structure, making them different from others. The elements that make up these materials usually have similar electronic configurations, having one or two valence electrons. These electrons do not get involved in chemical bonding and are free to move from atom to atom without much of a trouble due to repulsion from other electrons. Scientists refer to this general phenomenon as the sea of delocalized electrons, and it is present in any kind of metallic bonding. An electron inside a metal is able to flow from one place to another in equipotential paths. In other words, it moves in such a way that its net energy doesn't change as long as it stays within the metal. You can think of it as if the electron was a particle trapped in a box with a constant potential energy, but that potential energy function would have a higher value outside of that box, so removing it from the metal would require the energy difference of both states. That energy difference is known as the work function of the metal, but in order to fully understand its behavior, we have to talk about some properties of electrons first. As we already know from past lectures, electrons can occupy discrete energy levels in atoms, filling the gaps from lowest to highest values until all the electrons of a material are added. Each energy level can be identified by a set of quantum numbers, but we may have a problem. There may exist more than one set of quantum numbers that refer to the same energy level. In quantum mechanics, we say that these energy levels are degenerated. We have a particular interest in determining the probability of an electron occupying a given energy level, so the fact that there are different states that share the same energy level plays an important role in the calculations. We may start by proposing a function that describes the number of allowed states for a given energy and the probability of that state being occupied. The resultant function plots something that looks like this. This graph is the product of the Fermi-Dirac distribution and the function that describes the density of allowed states. There is a special point in the graph. The last electrons to be added, considering that such electrons have no extra thermal energy, will have the highest energy of all. In our model, the Fermi distribution of probability also converges to 50% when we consider thermal contributions. We call this point the Fermi level, and it's important because this energy level is in fact the energy level of the electron in the box that we talked about in the beginning.
Well, let's see a typical energy diagram for a metal. The bottom of the conduction band is taken as a reference level of zero potential. Electrons in the metal experience a constant confining potential of deep U. Possible quantum states for these electrons are represented as horizontal lines and all fill up to the Fermi level. The ejection of electrons from the surface takes place in those who have energy inside the solid in an initial state near or equal to the Fermi energy. To be emitted, electrons need an additional amount of energy denoted by W, and as we said previously, it is called the work function. This extra energy depends on the composition of each material and can be obtained, in the case of thermionic emission, by heat energy, or for example in the case of photoelectric effect, by an absorbed photon. Electrons that can escape from the metal need to have an energy equal or greater than the sum of the Fermi energy plus the work function. In other words, we need to take into account that only those electrons with a huge momentum component normal to the surface of the metal can escape from it, having the relation momentum in the normal direction squared over 2m must be equal or greater than the Fermi energy plus the work function. Then we can rewrite in terms of the velocity in this direction. So whenever this x component of the velocity is greater than this relation, the electrons will overcome the surface forces to contribute to a current saturation density emitted by a cathode. With this knowledge, a temperature-dependent saturation current density can be calculated as Owen Richardson, a British physicist, did in 1901.
The laws governing the behaviors of electron emission include Richardson's law for thermionic emission. Most any thermal process is governed by the Boltzmann factor. The Boltzmann factor expresses the relative probability for an event requiring energy E in a system at absolute temperature T. Clearly, if the energy is much greater than the Boltzmann constant times the temperature, the probability of the event happening is low. If an electron requires a certain energy W, called the work function, to escape from the metal, the Boltzmann factor suggests that this will happen with relative probability. Therefore, you should expect that the current will be proportional to the Boltzmann factor. Clearly, you should expect different elements to have different work function, just as different atoms have different ionization potentials. What is surprising is that the proportionality factor in the above equation includes a universal constant. That is, a constant that just depends on the properties of electrons, and most importantly, Planck's constant, and does not depend on the type of material. Thermionic emission proves the quantum state of electrons statistically, whereas the photoelectric effect proves much more the same physics electron by electron. The next level problem is to explain why this universal constant in fact does depend a bit on the material.
Let's see some applications. The first application of this phenomenon was thermionic bulbs, also called vacuum tubes, and were invented by John Ambrose Fleming, an English physicist, in 1904, based on the models that Thomas Edison patented in 1883. The vacuum tube contains a filament called cathode, surrounded by a plate, the anode, both sealed in an evacuated glass envelope. When hot, the emission occurs and there is a current flow to the anode if it has a positive potential. The current goes only in this direction because the plate or anode is not hot and doesn't emit electrons, being useful for rectification, for example, of an alternate current to a pulsating direct current. Another application is an electron gun. It is mainly used in cathode ray tubes for old computer monitors, televisions, and ionization of particles. It is a specialized vacuum tube. It starts with a small filament that hits the cathode. Two anodes turn the electrons emitted into an accelerated beam, and finally it is focused by an electric or magnetic field to hit the phosphors in the screen that emits colors in each pixel and form the image.